Welcome to Unit 4, Lesson 4, Part 2, Related Rates. In this section, we'll be addressing Topic 4.5 from the 2019 course and exam description, Solving Related Rates Problems. The standard for this lesson is CHA-3.E.1. The derivative can be used to solve related rates problems, that is, finding a rate at which one quantity is changing by relating it to other quantities whose rates of change are known. Our instructional objective is that students will be able to interpret related rates in order to solve problems in applied contexts. Our inquiry question is still, how can derivatives allow us to solve real-world problems involving related rates? The derivative dy dx of a function y equals f of x is its instantaneous rate of change with respect to the variable x. When a function describes either position or distance, its rate of change is interpreted as velocity. In general, a time rate of change answers the question, how fast is a quantity changing? For example, if v is volume that is changing in time, then dv dt is the rate or how fast the volume is changing with respect to time. If a person is walking toward a street lamp at a constant rate of 3 feet per second, then we know that the distance is decreasing. And so dx dt would be equal to negative 3 feet per second. If they walk away from the lamp, the distance is increasing and the rate of change becomes positive. dx dt equals 3. Let's look at a framework for solving related rates problems. Step 1, we're going to make a sketch and label the quantities. In Step 2, we'll read the problem and identify all quantities as something we know, something that's given, or something that we need to find with the appropriate information. In step number 3, we're going to write an equation that involves the variables whose rates of change are either given or are to be determined. In step 4, we'll use the chain rule to implicitly differentiate both sides of the equation with respect to time. This was the step that we focused on in the last lesson, Unit 4, Lesson 4.1. In step 5, we substitute into the resulting equation all known values for the variables and their rates of change, and then we solve for the required rate of change. Let's look at example 1. Suppose x and y are both differentiable functions of t and are related by the equation y equals x squared minus 3x. We're asked to find dy dt when x equals 3, given that dx dt equals 2 when x equals 3. In this example, we don't have a physical context, and so we are actually starting with step number 3, write an equation. We've already been given the equation. So let's write this equation, y equals x squared minus 3x. And in step 4, we differentiate implicitly using the chain rule. And so the derivative of y is dy dt, and that's going to be equal to 2x times dx dt minus 3, and the derivative of x is 1 dx dt. So we have dy dt is equal to, and we can factor out the dx dt, so we can rewrite this as 2x minus 3 quantity times dx dt, and that's going to be our derivative. But now they want us to find the value for this rate of change when x equals 3. So we have dy dt evaluated at x equals 3, and so that's going to be equal to 2 times 3 minus 3 times dx dt, and they tell us that at x equals 3, dx dt is equal to 2. And so 2 times 3 is 6, 6 minus 3 is 3, times 2 is 6. And this is going to be our answer. Now in example 2, we have a problem in a physical context, and so we're going to begin with step 1 and try to draw a picture that represents the situation. So a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? So start by drawing some concentric circles. Okay, so here we have our pebble dropped into a calm pond. The concentric circles are representing the wavelets that are moving out away from the center. Now the next thing that we want to do is read back through the problem and then identify what we know, what's given, and what we need to find. Alright, so a pebble is dropped into a compound causing ripples in the form of concentric circles. Got it. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So one thing I know is the area formula for a circle. And so let me start with that. Area is equal to pi r squared. Now let's look and see what we're given. We're told that the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. And so we can express that as dr dt, change in radius as a function of time, is equal to 1 foot per second. Now let's see what we've been asked to find. When the radius is 4 feet, at what rate is the total area changing? So we're looking for dA dt evaluated at r equals 4 feet. So we have a relationship between area and radius. Let's go ahead and differentiate this. And so we're looking for d dt of the area equal to d dt of pi r squared. And that's going to give us dA dt equals 2 pi r dr dt. Now what we're looking for is dA dt evaluated at r equals 4 feet. So that'll be 2 pi times 4 times dr dt, which was given as 1. So this is going to be equal to 8 pi, and this is a change in area per unit time, and so it's going to be square feet per second. In example 3, we're told air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute. Find the rate of change of the radius when the radius is 30 centimeters. So let's draw a picture of this situation and label the important parts. Alright, so here's our sphere with its radius, and we're told that r is equal to 30 centimeters. That's going to be the time that we're interested in. Alright, next, let's think about what we know, what we're given, and what we need to find. So they tell us that air is being pumped into a spherical balloon, and so that means that the volume of the balloon is going to be changing. And we can find the volume of a sphere in terms of its radius. They've asked us to find the rate of change of the radius when it's equal to 30 centimeters. So let's start with the volume formula for a sphere. So V is equal to 4/3 pi r cubed. Now we're given that the change in volume is a positive 800 cubic centimeters per minute. So that's going to be dV dt equals 800, and that's cubic centimeters per minute. And we've been asked to find dr dt, and we want to do that when the radius is equal to 30 centimeters. Alright, so let's begin with our volume formula, and let's differentiate this. So we have V equals 4/3 pi r cubed, and that means that dV dt is equal to 3 times 4/3, the 3's cancel and we get 4 pi r squared times dr dt. So next, let's substitute what we know into our new equation. So remember that dV dt is 800 cubic centimeters per minute, and that's going to be equal to 4 pi times the radius, which is 30 centimeters squared. So the 30 is getting squared and the centimeters are getting squared, times dr dt when r equals 30 centimeters. So now we have an equation that we can solve for dr dt. So we have dr dt when r equals 30 centimeters is going to be equal to, and it's going to be 800 divided by, and we're going to divide by all of this, 4 pi times 30 squared. And this is centimeters cubed per minute divided by centimeters squared. So 30 squared is going to be 900 times 4 is 3600 pi. And so 800 over 3600 is going to simplify to 2 over 9. And so this is going to be equal to 2 over 9 pi. And the units here, centimeters squared, is going to cancel with centimeters cubed, leaving centimeters per minute. And that's going to be our rate of change when the radius is 30 centimeters. Let's look at example number 4. They tell us the top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what is the rate of change of the distance between the bottom of the ladder and the wall? This is a very famous problem from AP Calculus exams past, and it's one of the free response questions that is probably most studied and is representative of AP questions for related rates. Let's begin by drawing a picture of this situation. Alright, so we have a 25-foot ladder that is leaning against a wall, and it's beginning to slide down. And as it slides down, the y value is changing, and at the same time, the x value is changing. Notice that the length of the ladder, of course, does not change. It stays 25 feet. Let's go back and look at the problem and identify what we know, what's given, and what we need to find. Well, one thing that we know is that it's a vertical wall, and that tells us that we have a right triangle. And so since we have a right triangle, we can create a Pythagorean relationship. So we have x squared plus y squared is equal to 25 squared. Now let's see what we're given. We're told that the top of the ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. So if the top of the ladder is moving down at 3 feet per minute, that's going to be a change in y as a function of time. So let's express this rate as dy dt equals -3 feet per minute. Let's see what we're looking for. When the top of the ladder is 7 feet from the ground, so that means when y equals 7, what is the rate of change of the distance between the bottom of the ladder and the wall? Well, the difference or the rate of change of my distance between the bottom of the wall and the ladder, that's dx dt. So we're looking for dx dt evaluated when y is equal to 7 feet. Now, by the way, a common notation is to demarcate feet using a prime or an apostrophe, but I like to avoid that because we use primes for derivatives, so I'm just going to write out feet instead of using 1 prime for feet and 2 primes for inches, etc. Now let's take our equation and differentiate this. So differentiating, we have 2x times dx dt plus 2y times dy dt is equal to, and the derivative of 25 squared is 0. Now we're looking for dx dt, so I think what I want to do is to solve this equation for dx dt. So we get 2x dx dt is equal to -2y dy dt. And then dividing through by 2x, we have dx dt is equal to, and the 2's cancel, and so we have -y over x times dy dt. Now finally we're looking for dx dt when y equals 7. So dx dt when y equals 7 feet is going to be equal to negative y, which is 7 feet, divided by x. And it's at this point that you may realize we don't know what x is whenever y is 7, but we can figure that out because we have an equation that can let us solve for x when y is equal to 7. So using our Pythagorean relationship, let's go off to the side and find out what x is when y is 7. So we have x squared plus 7 squared is equal to 25 squared, and x squared plus 49 equals 625, and this implies that x is going to be equal to plus or minus square root of 625 minus 49, but since we only need the positive root, we'll just look at the principal square root. So we have the square root of 576. And I'm not going to do any rounding until we get to the end of the problem. Now this is being multiplied by dy dt. And remember we were told dy dt was negative 3 feet per minute. So negative 3 feet per minute. Over here, these feet cancel, and now we have a negative times negative is a positive. 3 times 7 is 21 over square root of 576 feet per minute. And the square root of 576 is 24. So we have 21 over 24 feet per minute. 3 goes into 21 7 times. 3 goes into 24 8 times. So 7/8 feet per minute. And if you express that as a decimal, don't forget you need 3 decimal places accuracy. In example 5, we're told that at noon, ship A is 150 kilometers east of ship B. Ship A is sailing west at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? Let's start by drawing a picture based on this problem. Alright, so here we have a picture laying out a triangular relationship based on cardinal directions. So the vertical axis represents our northerly direction, and here we have our east to west relationship for ship A. Now notice that at time t equals 0, both ships are on the x-axis. B has not yet started sailing, A has not yet started sailing, and they are separated by a horizontal distance of 150 kilometers. So let's call the distance that B travels during the 4 hours elapsed since noon to 4 o'clock. Let's make a note that T is going to be equal to 4 hours. So during that amount of time, B is going to travel Y. And the question is, how do we describe what this distance is as it's changing? Well, at 4 hours, A will have traveled a distance, let's call it X. And so that means that the length of this line segment is going to be 150. That was the starting distance. Minus X. We have to subtract that distance traveled because this is getting smaller. A is traveling to the west. And let's go ahead and call our hypotenuse here Z just to be consistent. Now, what I know is the Pythagorean theorem. So we have A squared plus B squared equals C squared, which in this case is going to be 150 minus X quantity squared plus Y squared is equal to Z squared. Now let's think about what information they gave us. They told me that ship A is sailing west at 35 kilometers per hour. Well, okay, so you know what? When we subtracted the distance here, we took care of. So I'm going to put the speed. This is going to be a speed, not a velocity. It's not assigned value. So we're going to put dx dt is equal to 35 kilometers per hour. Now the other thing we know is dy dt. dy dt is the rate of change for ship B, and that's going to be 25 kilometers per hour. Now what they've asked us to find is dz dt, the rate of change of the distance between ships A and B at 4 p.m. So that's going to be when t is equal to 4 hours. Let's start with the equation that we derived from the Pythagorean theorem. So 150 minus x quantity squared plus y squared is equal to z squared. And let's differentiate this implicitly. So using the power rule, we have 2 times 150 minus x times the derivative of the inside, which is going to be times -1 times dx dt plus 2y dy dt is equal to 2z dz dt. And immediately I'm going to go ahead and multiply through this equation by 1/2, and that's going to cancel these 2's for me. And let's rewrite this. So now we have negative 150 minus x dx dt plus y dy dt equals z dz dt. So let's look at this equation and take stock. I know what dx dt is. I know what dy dt is. I'm looking for dz dt, but I still have an x, a y, and a z that I have to plug into this equation, and I don't know what those values are. Well, here's the clue. X, y, and z are going to be the distances that happen in this triangle when t is equal to 4 hours. So let's go off to the side and just kind of think about what's going on here. You know, velocity is equal to distance over time. And so what that means for us is that distance is equal to velocity times time. And so let's take these speeds, these rates of change, and let's multiply by 4 hours and find out what the distance traveled is. And so x is going to be equal to 35 kilometers per hour times 4 hours. Y is going to be 25 kilometers per hour times 4 hours. And let's see, this is going to be 140 kilometers. Hours cancel, and this will be 100 kilometers. So at t equals 4, I have x and y. Need to find z. And so let's plug into our relationship. And so we end up with 150 minus 140 squared plus 100 squared equals z squared. Solving for z, we'll take the positive square root, and 150 minus 140 is 10. 10 squared is 100. 100 squared is 10,000, and so we get the square root of 10,100. Factor out 100, take the square root, you get 10. So z is equal to 10 on radical 101. And that'll be the exact value. All right, so let's go back to our equation here and substitute everything. And this is going to give us negative 150 minus 140 times dx dt, which is 35, plus y, which is 100, times 25 equals 10 radical 101 dz dt. Okay, 150 minus 140 is 10 times 35 is 350, so this is negative 350 plus 2500 equals 10 radical 101 dz dt. So dz dt evaluated at t equals 4 is equal to 215 divided by the square root of 101 kilometers per hour. Okay, so this is an exact answer with, don't worry about rationalizing the denominator. If you do report this as a decimal, make sure you use 3 decimal places. Let's look at example 6. Here we have a right circular cylinder changing shape. The radius is decreasing at a rate of 2 inches per second, while its height is increasing at the rate of 5 inches per second. When the radius is 4 inches and the height is 6 inches, how fast is the volume changing? Let's start with a picture. Alright, so here's our cylinder, and it has a radius r, and it has height h. Now we're given that volume is equal to pi r squared times h. That's our formula, and so that's actually what we know. We know that volume equals pi r squared times h. Now let's see what we're given. They say the radius is decreasing at a rate of 2 inches per second. So that's going to be dr dt, negative 2 inches per second. And that's not the only thing we know. They tell us the height is increasing at a rate of 5 inches per second. And so we have dh dt equals positive 5 inches per second. Now let's see what we should find. It says when the radius is 4 inches and the height is 6 inches, how fast, in other words, what is the rate of change of the volume? How fast is the volume changing? So we're looking for dv dt. And now we're evaluating at 2 different parameters. They want the radius to be equal to 4 and the height to be equal to 6 inches. So let's start by differentiating our volume formula. dv dt is going to be equal to pi, and we're going to have to differentiate r squared times h using the product rule. And so this will be the first, r squared, times the derivative of the second, which is dh dt, plus the second, which is h, times the derivative of the first, which is 2r dr dt. So let's substitute in, and we have dv dt is equal to pi times r squared. So remember that r is going to be 4, so that's going to be times 4 squared is 16 times dh dt. dh dt is 5 plus h. h is 6 times 2r. r is 4. 2 times 4 is 8. Times dr dt, negative 2. So dv dt, let me go back and make sure I indicate what I'm evaluating. r equals 4, h equals 6. So this ends up giving us negative 96 pi plus 80 pi, and that ends up giving us negative 16 pi, and my units are cubic inches per second. And you can leave your answer in terms of pi, but again, if you substitute, make sure you round to 3 decimal places. In example 7, we have another famous problem from AP Calculus exams in the past, the inverted cone problem. Here we have an inverted cone leaking water at a rate of 1 centimeter cubed per minute. The cone has a height of 9 centimeters and a diameter of 6 centimeters. Find the rate at which the water level is dropping when h equals 3 centimeters. Let's start by drawing a picture of our inverted cone. So here we have our right inverted cone with radius r and height h. And we can actually simplify this problem by getting it in terms of either r or h by itself and only have one variable to deal with. And the reason is because the radius is going to change as a function of the change in height. So let's take our triangle and just remove it from the cone. So if we look at this triangular cross-section, we can see that the radius of the water level and the height of the water level, this gives us a similar triangle relationship. So cone has an overall height of 9 centimeters and an overall radius of 3 centimeters. They tell us the diameter is 6. And so this allows us to set up a proportion based on similar triangles. 3 is to 9 as r is to h. And if we solve for r, this is going to give us h over 3. Okay, back to what we know, the volume formula. So V equals 1/3 pi r squared times h. And we're giving that the cone is leaking water. So if the cone is leaking water, that's actually going to be a change in volume. And they tell us the rate for that change in volume is 1 centimeters cubed, and since it's leaking, that'll be negative. So we have that dV dt is negative 1 centimeters cubed per minute. They want us to find the rate at which the water level is dropping. Well, the rate at which the water level is dropping, that's going to be a change in the height of the water level. So what they're talking about here is dH dt. And they want us to find dH dt when h is equal to 3 centimeters. Let's differentiate our volume. Well, before we differentiate this, let's substitute for r and see if we can get a simpler version of this. So V is going to be equal to pi over 3 times r squared, but r is h over 3, so that's h over 3 squared times h. And so let's see, that'll be h squared times h is h cubed, so pi times h cubed over, and 3 squared is 9 times 3 is 27. So V equals pi h cubed over 27. So this is what I want to take the derivative of. So V equals, and we'll write it as pi over 27 since that's the constant, times h cubed, and this will be a lot easier than differentiating with a product rule. So we have dV dt is equal to 3 pi over 27 times h squared times dH dt. And so 3 goes into 27 9 times, so we have pi over 9 times h squared dH dt. So if we substitute in for dV dt, that's going to give us negative 1 equals pi over 9 times h squared, well h is 3, so 3 squared is 9, times dH dt when h equals 3. So the 9's cancel, and what we find is that dH dt at time h equals 3 is equal to negative. So dH dt evaluated at h equals 3 centimeters is equal to negative 1 over pi centimeters per minute. And this is an exact answer, but if you do get a decimal approximation, don't round until the end and make sure you've got 3 decimal places. In example 8, we're told a lamppost is 26 feet tall. Andy Great is a 6-foot tall calculus teacher and is walking away from the lamp at a rate of 4 feet per second. When he's 20 feet away from the lamppost, find each of the following. And so part A, they want to know how fast is the length of the shadow changing. Okay, so this is another similar triangle problem. So we've already got a picture. Let's start labeling it with things that we know. This is Andy is 6 feet tall. The lamppost is 26 feet tall. I don't know how far he is away from the lamppost at any particular time. We're interested in what happens at 20 feet, but this is changing, and so I need to model it with a variable. So let's call his distance from the lamppost x. Now the length of his shadow is the remainder of this triangle, so let's just call that y. So here's Andy's shadow, and we're going to call that y. So let's set up our similar triangles. So we have 26 over 6. 26 over 6 is going to be equal to the total length of the base, which is x plus y, divided by y. Now let's clear fractions, and so we'll multiply through by 6y. And when we do that, the 6's cancel and we're left with 26y. And over here the y's cancel and we're left with 6x plus 6y. Combining like terms, we can subtract 6y from both sides. We get 20y is equal to 6x. And solving for y is equal to 6 over 20 times x, 3 over 10 times x. Now if we differentiate this, we get dy dt equals 3/10 times dx dt. Now we were given that Andy's rate of walking, the rate of change was 4 feet per second. So that gives us 3 over 10 times 4. And 12 over 10 simplifies to 6 over 5. And our units are feet per second. So just to clarify, dx dt was the rate of change of x. dy dt was the rate of change for the shadow. Now in part B, they ask, at what rate is the tip of his shadow moving? Well, the tip of his shadow, remember, Andy is x feet away from the lamppost at any given time, and the length of his shadow is y feet at any given time. The height of the lamppost is 26, Andy's height is 6. So when they ask about the rate that the tip of his shadow is moving, that's going to be the sum of the two rates that correspond to his distance changing dx dt and the length of his shadow changing dy dt. So we're wanting to know what is the total rate of change for this side of the triangle as Andy is walking. And so we can write that as dx plus y. So the rate of change in x plus y as a function of time, and that is equal to the sum of dx dt and dy dt. And so dx dt was given to us in the problem. Dx dt was 4 feet per second. And in part A, we found dy dt. That was 6/5 feet per second. So let's get a common denominator, and we have 20 plus 6 over 5 feet per second. That's 26 feet every 5 seconds. So therefore, the tip of Andy's shadow is increasing at a rate of 26 feet every 5 seconds.